Thank you very much for the kind introduction. So you pretty much heard everything about me that I have on this slide anyway, but I'll go through it. So as you heard, I got my PhD from Germany in 2018. I joined Argonne right away. I worked at LCF before and now at MCS. So since 2018. And since 2014, I work on LLVM and the LLVM compiler framework in a lot of different places over the years. And for a few years, I'm part of the OpenMP Standards Committee. Recently, like last year, I became the official LLVM OpenMP code owner for offloading. So if you have questions about OpenMP offloading, feel free to just shout them out. And that's it. If you, during the talk, have any questions of any kind, please just unmute and ask. That is the easiest. I'll try to ask sometimes for questions. Try to stop, but feel free to just unmute and ask your questions. If you don't want to do that, put them in the chat. That also works, and we'll figure it out from there. Okay, so what I'm going to present today is kind of the works that I'm involved in, but it's obviously not only stuff that I do by myself. The LLVM OpenMP effort is a community effort. First and foremost, we have people from academia, like labs and universities, industry, and power users. And the bold people here are people that are co-authors on the papers that I'm going to present, or of which I'm going to present ideas and results. But there is obviously quite a few people that are missing here, also co-authors missing, and so on and so forth. So just to keep in mind, this is not like my work, it's just things I present where I was involved in. Now, I'm going to kind of go through more or less these papers and some ideas and results of those. If you are interested in looking them up later, you can find them on my Scholar page. You can screenshot this. It's probably pretty easy to Google this. And if you want to learn more, there is a couple of presentations online that are very recent and have good content for link time optimization in JIT. There is one on YouTube, and there is one about a compiler's view of OpenMP that gives you kind of an intro of how the compiler and offloading and so on in OpenMP works. Okay, let's get started. When you think about OpenMP and LLVM, what you probably think about is Clang, the C family compiler frontend that allows you to compile C, C++, CUDA, HIP, SYCL, OpenCL, and all of that. And inside of Clang, there is an OpenMP parser for the pragmas. There is an OpenMP semantic analysis that determines if what you wrote makes sense. And then there is a code generation that translates to pragmas and everything else OpenMP into something that the runtimes can handle. So if you think about OpenMP and LLVM, this is probably the first that comes to mind. But there's also the OpenMP runtime, which is something you probably have seen in LLVM. That runtime is called libomp. It's a classic OpenMP runtime. It runs on the host, and that is kind of what you see here is kind of the state-of-the-art OpenMP 3.0. Now with 4.0, we got offloading, and then the OpenMP runtimes were extended to have this libomp target, which is a runtime for offloading, plus plugins, which allow you to add new backends, for example, new GPUs or new offloading devices, like, for example, an NAC vector unit. And then the device runtime, which is the part of the runtime that actually runs on the GPU or whatever device you have and provides you with the functionality necessary for OpenMP on that device. So libomp is the classic host runtime. Libomp target and the plugins run on the host to make the communication about to regulate all the offloading and do all the communication with the devices and the drivers. And libomp target, in this case, libomp target MVPTX or libomp target HSA, they run on the device side. Now, this is kind of OpenMP 4.5. But then we kind of realized we're going to have a second front end that will understand OpenMP. So we're developing this Fortran front end called Flying. And the Fortran front end will also have an OpenMP parser, an OpenMP semantic analysis, and an OpenMP code generation. Instead of duplicating everything, we kind of started this effort of an OpenMP-IR builder, which helps you to generate, which helps you to leverage the codegen part from Clang in Flang, and also allows non-OpenMP users to utilize the OpenMP runtimes and environment. So if you, for example, write a Julia code or Chapel, and you want to use the OpenMP offloading infrastructure, you can, like through the OpenMP builder, you kind of can do that much easier than whatever you had to do before. Generally, we favor now a simple IR that we can analyze and optimize better. And why do we do that? Because we have added yet another component recently over the last 2 or 3 years. That's called the OpenMP optimization pass, OpenMP-Opt. It runs in LLVM by default when you enable optimizations, and it will only run on your OpenMP code though. So if you use OpenMP, this pass will run, and it has specific OpenMP-aware optimizations for both the host and the device. So it knows about OpenMP runtime calls, it knows about how GPU compilation happens, and it can transform things. And we're going to see a lot of examples later on. So this gives you an overview of the entire OpenMP infrastructure, the ecosystem inside of LLVM. So it's way more than just the front end and the parser or the one runtime. It's like a whole lot of things. So let's take a look at some initial problems that we had like a few years back when we started all this. Like there were debugging challenges. So developing and debugging OpenMP at the point was really hard. You didn't really know what was going on. You had OpenMP had indirection overheads that we identified, and the general GPU performance wasn't great. And we're going through those points now. So first, debugging challenges. So back in the day, if you run your OpenMP device code, especially on a GPU, and it crashed, all you got is a very obscure error message that something crashed, and that was it. If you do it nowadays, what you get is the same obscure error message, which is the first bold thing here, an illegal memory access was encountered, which basically just says it's a seg fault, a memory access that seg faulted. But it says 2 more things here, which are important. One is it tells you to consult the web page, which has debugging options, and we'll see them in a second. And the other thing is it even gives you like the source location, and it gives you more information if they are available. So this already helped quite a bit to realize, okay, where did it fault in the first place? Because that was hard. And then let's look at the additional debugging options here. So one of the options is libom target info. That's an environment variable that is always available to you to ask the offloading runtime about what is going on. So it's a bit field, so you set the different bits. And what you do is, what it does, depending on which bits are set, it emits information during the runtime, during the run. And what you see here, we set like multiple bits, and then we run the sum executable, and it tells us, okay, it's executing, you know, the sum at the OpenMP kernel at row 5 with 3 arguments, and it has a first private n, and it has a to from sum that is implicit because it's a local variable, and it has a to of an array, and it tells you how big they are, and then it says, okay, now we're copying data because we need to do that. And then it says, okay, now we launch the kernel with that many blocks and that many threads in SPMD mode. So it gives you all that information, and it can even emit more. So this is really helpful to understand what's going on, what data is mapped, what data is updated, how is the reference count tracked, and so on and so forth. And when it crashes, you can even emit the mapping table, for example, as soon as like the error is detected, it can emit the mapping table, so you know what has been mapped, maybe what you forgot to map, and so on and so forth. We have a question. Would it also work for frameworks like Number, which provide an OpenMP option? Yes, Number can emit through that more easily LLVM IR that right away does that utilizes OpenMP. So they could go that way to utilize OpenMP. I would have assumed they're probably right now doing their own abstraction layer. But to be honest, I don't 100%, I don't know for sure. I know that the Chapel people are actually looking at using the OpenMP IR builder to utilize the offloading infrastructure that we have. Yeah, so the last thing on the debugging options is the GPU runtime checks. Here, the GPU runtime checks are actually enabled through two separate configuration options that have to come together. So at compile time, you see the first line here, the bold part, you have to set a command line flag that says, hey, I want debug option with bit 5 set, or with the bit set that corresponds to 5, right? With the bits. And then at runtime, you again have to say, hey, now actually emit the debug information for the bits that correspond to 5. There's two options instead of one because the GPU runtime checks are actually expensive, or at least they can be. And if you do not provide the compile time option, we completely eliminate them. So they don't add any cost to your program. But as soon as you provide the command line option, they are enabled and you can actually utilize them. And then you enable them, and then you can actually activate them at runtime through the debugging option here to the environment variable. And what you see here is it actually says, oh, by the way, the shared memory stack that we use for that we use for local variables that are allocated and potentially shared between threads is full. We have to, and that is usually a sign of problem, and it will always make your program slower. And then the next thing it prints here is it says, oh, by the way, we call it malloc, and we needed new memory, so we called malloc, but malloc returned a null pointer. And at this point, it actually will going to crash. But now you know, oh, wait a minute, malloc returned a null pointer. That is why it crashes. So it's not like you mapped something wrong, but just, you run out of memory is basically the thing here. So we have various of these target debug options, these runtime checks now, including also tracing on the device and so on. So all of this is kind of integrated such that you have a more help trying to debug and understand what's going on. That brings me to the second point, indirection overheads. So very, very early on in 2018, we actually looked at the execution of OpenMP programs and how the compiler optimizes them. So take a look at the program on the left. What you see here is a variable y that is initialized to 7, and then it's used inside of a loop and after the loop, right? And what you expect your compiler to do is to just replace y with 7 because it is never changed. So it's just 7, so we don't need y. We could just put 7 everywhere and we're done. And any compiler you probably can use for C, C++ is going to do this, and you're happy, all is good. But now what happens if you put this loop, if you make this loop a parallel, OpenMP parallel for loop, and it's not necessarily an OpenMP thing. Any sort of parallelism will introduce indirections, and those indirections are going to hurt you now because if you do this, by default, what will probably happen is that neither the y inside the loop nor the y after the loop is going to replace by 7. And that's kind of unfortunate. So using this parallelization makes your optimization, blocks optimizations, but not only for the parallel regions, but also for the surrounding code, because this G of Y has nothing to do with the parallel loop, right? And we kind of noticed that, and when we wanted to know, is this actually a problem? So we did an experiment. What you see here is the two results of that experiment. And it's for left on the Pathfinder and right for SRED. There's 2 benchmarks from the Rodinia benchmark suite. Now, what we did is we executed this in 2 different versions. One version on the left is base sequential. Base sequential is just the version as it is in the benchmark suite without OpenMP. So we compiled it as sequential code and then we run it. That is base sequential. Base parallel, base part is on the right, is the version with OpenMP, but we execute it with a single thread. So it's an OpenMP program that is executed by a single thread. So both of those programs are executed by a single thread, but the left one doesn't have OpenMP and the OpenMP implied indirections, and the right one does. And what you see here is that the performance suffers a lot. So we get like 40% performance penalty on Pathfinder. On SRAD, the performance is like more than twice as bad. That's obviously a problem. I mean, parallelization gives you scaling and you might make up for it, but making your program first really slow in order to then speed it up through more cores is not necessarily a great idea, right? And now people often suggested back then and even today, oh, this is probably, you know, OpenMP runtime. You have to go like all these runtime calls and you call into the runtime and it takes time to set everything up and so on and so forth. But we were not really sold on that idea that it's the runtime really. So what we did is we looked again at these missed optimization opportunities and we helped LLVM to perform two key optimization in the presence of OpenMP parallelism. And here you see the results of that. I'm not going to go into much detail because of time reasons, but here you see the results. On the far left, the first two bars, or the first two plot parts, is what I showed you earlier. This is the SRAD benchmark with base sequential and base parallel on the far left. So 143% slowdown. And then you see the sequential and parallel versions here with additions to LLVM. So attribute deduction addition is the first one. ArgP is argument promotion. And in the end, the last two on the right are both enhanced attribute deduction and argument promotion that are aware of OpenMP. And all you have to take away from this is that if we make those two LLVM passes aware of OpenMP and able to look through the indirection of OpenMP, the parallel version here, which is on the far right, that is the version that has OpenMP but runs with a single thread, is as fast as the base version, which doesn't have OpenMP. So the entire slowdown of 143% goes away. It has nothing to do with the runtime. It's only about the missed optimizations that the compiler couldn't do or didn't do because of the indirection introduced by OpenMP. And we can actually get these optimizations back if we make the compiler stronger and or aware of OpenMP. And that's kind of the idea here. And everything that kind of follows from now on follows that same conceptual idea. Let's take a look at what the problem is and then make the compiler stronger and able to kind of interact with the user in order to make the programs faster and like eliminate all the overheads, all the indirection overheads that we otherwise had. Okay, any questions so far? No. Okay, let me go through the next one. So this is one of the first optimizations that we did really for GPU execution. And conceptually, the problem here is that OpenMP is meant for CPUs, while GPUs run differently. And oh, sorry. How did that happen? Someone managed to close it. Sorry. Okay. Or not. Come on, Google Slides. All right, great. So OpenMP was initially developed for CPUs, and GPU execution model is different. And if you look at this CUDA code here, you can kind of see that it's different. So for example, the user explicitly knows that all the threads run all the time and they put this buffer that is supposed to be used by multiple threads, they put it explicitly into shared memory. And then they have these conditionals that check which thread should execute something. For example, this single-threaded init code, and they explicitly place barriers, so to synchronize threads, and so on and so forth. So users are aware that all the threads run at the same time, and then they place barriers, they place thread conditionals, and they also put memory into the appropriate locations, in this case, shared memory. Now, if you look at OpenMP, this is roughly the equivalent in OpenMP, and it looks a little different. And I have like made these comments here. So on the outer level, you have this explicit target teams distribute, which is kind of fine. And then you have the loop over the grid with block sizes, so for each team, which is also kind of fine. So this is implicit in the CUDA case, but that's not much of a difference. But then in OpenMP, you would simply write double buffer, because you could put it in shared memory, but people would, say, okay, this is only executed by a single thread. Why would I have to do anything? This is just single-threaded code. And in OpenMP, that is conceptually correct. The teams construct gives you a new team, but only one thread is active until you hit a parallel, which is completely different from the CUDA model and the GPU execution model. Therefore, there is also no conditional around this single-threaded init and no synchronization after, because there is only conceptually a single thread, right? And then you have these OpenMP parallels for the block size later on, which then activate all the threads and execute some code in parallel. Okay, so these two are roughly equivalent, roughly. But the performance on the OpenMP one is far worse, far worse. So what we do now is I'm going to through a couple of steps on how to get the CUDA performance from the OpenMP one. But the first thing we actually do is we're going to lower this OpenMP code to what it is, how it is implemented. And that will actually pessimize things first. So if you look at the double buffer and this variable L, what happens actually is we are allocating them dynamically. These are not local variables anymore. Why? Because local and stack variables cannot be shared across different GPU threads. But OpenMP allows you to share local and stack variables across different threads. On the CPU, that was never a problem. And once we got GPU support, nobody changed it. So this is explicitly allowed in OpenMP. It's forbidden in CUDA. So CUDA doesn't care. In CUDA, you have to deal with it yourself. But in OpenMP, we have to deal with it. So we explicitly allocate these in memory that is accessible by all the threads, rather than in local, rather than having it local variables or local arrays. So this is the first thing that happens. We actually globalize these locals. And then, but from here on now, we can start to do optimizations, compiler analysis and optimizations to improve performance. The first thing we want to do is we want to match the execution mode of the GPU, which is this SPMD execution mode, where every thread, the green arrows on the left, executes the entire kernel. While on the right, this is what the CPU execution mode looks, which is what we in OpenMP offloading calling generic, is there is a single thread that conceptually executes the entire code, and the other threads sometimes are non-existent. That's the red part. So only in a parallel region, all the threads will execute everything. And the rest of the code is only executed by one thread. But the problem is on the GPU, these red parts, these threads exist, they have to do something. So we have to deal with the fact that we have to make them inactive, reactivate them, and make them inactive again. And that is costly. So we really want to not do this mode, but want to do the SPMD mode. How do we do that? One thing at a time. First, we get rid of our globalized array accesses. So we analyze this buffer and this L to determine how it is used. And in this case here, we can determine that the buffer is used by multiple threads. or potentially used by multiple threads. So we actually allocate it in shared memory. And we can determine that the L variable is only used by a single thread. So it's thread local. So we actually allocate it in thread local memory. And doing so eliminates this dynamic allocation. So we now get the same allocations as in the CUDA case on the left. So this basically is equivalent on the allocation side. As a next step, we would do SPMization. Basically, we would push the parallel from inside the loop to the outside of the loop. And this allows us to start all the threads all the time, like at the beginning, run them all. And every time we hit something that is supposedly single threaded, we're going to have a conditional regarded, and we're having a barrier afterwards to synchronize all the threads again. And if you look at the left, this is what the CUDA code looks like, right? So we run all the threads all the time. And then if it's single threaded, we only get the first thread and we synchronize after to make sure all the threads see the update. So this is pretty much what the left looks like on the synchronization and single threaded part. And then next thing is, if the user tells us that we actually will have more teams than that we need to execute all of the blocks in the grid, and we have more threads than we have than the block size, so then we can eliminate those loops that were there. So go back. There's this outer loop over grid size, and there are these inner loops over the block size. If the user tells us we will have sufficient amount of threads and sufficient amount of teams, we don't need loops anymore. And this is basically what people usually assume in CUDA code. They assume they have a sufficient amount of threads, sufficient amount of blocks. So if the user tells us this is what we can assume, we can get rid of those for loops. And that really helps a lot. And then finally, we can eliminate aligned barriers if they're not needed. For example, this one here at the very end now, because there is no loop anymore, we know it's not needed, so we can eliminate that one. Now, this is kind of already very close to the CUDA code. But now, if we know how many blocks and grids we actually start, so if the user tells us, oh, the grid size is this, the block size is this, for example, through numteam's thread limit, or through other means, we can actually get rid of all these conditionals as well. So if we know the grid size and the block size, we can simplify this further. And what is left over is now actually equivalent to the CUDA code. This will execute the same thing. There's no difference anymore. And now your OpenMP code, after all these transformations, will perform exactly as your CUDA code. But you needed these optimizations to happen. Okay, so how does that look like with regards to performance? This is a quick evaluation. You see basis LLVM for LLVM 12, and then the one with the arrow, LLVM def, is the one you'll want to look at. And on benchmarks like XS bench and mini QMC, so upper left corner, lower right corner, we get speedups of 1.5 and 2.2x. On benchmarks like SU3 bench and RS bench, the speed up is more than 10x. And on RS bench, we now match the CUDA performance. On the others, not yet, but on the others, we're getting there. So this was kind of very important to get closer to CUDA performance, and on some benchmarks, we already match it. So the next thing we did is we co-designed an OpenMP GPU runtime, so the part that runs on the GPU, together with optimizations to get a portable GPU runtime that is optimized properly. And how does it look? If you think about a GPU runtime, it has some state. So it keeps some state. In this case, we just say, okay, there is the global variable in shared memory that's called state. And it keeps some state to organize things. And for example, it has to realize that at the beginning of a kernel, our team has a size of 1. And whenever we hit a parallel, the team size is increased, right? So first we initialize the state, and then we have a barrier, so everyone knows what the values are. and everyone agrees on them. And then we have this parallel runtime call where we pass in the user code in the outline function over here. And then inside that outline function, we assume we use the team size. So what's going to happen? First, let's look at the implementation of OMP parallel, which is actually going to conceptually start all the other threads in the team and make the team bigger. So what it does is, if we already have a team size bigger than 1, so we are actually inside of a nested parallel region, we'll just execute this parallel region sequentially. So we don't support nested parallelism really. I mean, it's correct, but it's not. We don't add more parallelism. Afterwards, we say, okay, the team size now is the entire block. Okay, so far so good. And then everyone executes this function, in this case here, the outline function. And then we're done with the outline function. We have another barrier there. And then we set the team size back to 1 because now it's again a conceptually sequential region. And then we have another barrier. So this is much simplified of what's going to happen, but it gives you an idea. So this is kind of where we start. And how do we optimize this? So what we do first is we use interprocedural reachability and the knowledge about shared memory lifetime to determine that this team size that we set here at the beginning of kernel hasn't been changed when we ask for it in OnParallel at the beginning. So we know already that the team size there is 1, and we can get rid of the conditional. That's the first step. In the second step, we use a similar reasoning with the interprocedural reachability, the shared memory lifetime, and the fact that we have interprocedural dominance. So to move this team size into the outline function. So if you look, function is executed here inside of OnParallel. We know function is actually the outline function, and the last assignment to team size before that was blockdemx. So we know the value we're going to read on there is blockdemx. So we're going to move this to the end. And then we realized that now team size is only written. It's never read. So we removed all the reads from it. So we can just remove team size. And in this example, the only state that we have left is team size. So we can get rid of all the assignments to team size because it's write only. We get rid of the state. And what's left over, what's left over is now a lot of barriers that actually don't have anything in between because there is nothing happening anymore. So we can get rid of these aligned barriers because they don't synchronize anything anymore. And once we're there, all is left to do is to do inlining, and because all of the abstractions now are empty. So we just do inlining, and what we end up with is really a kernel that just is really what the user code written. So what CUDA code would look like as well. All of the OpenMP abstractions that we had here to handle the state, handle the fact that certain code is sequential, other one is parallel, all of this is gone if we, like in the best case, and we get really fast kernel code out of it. We have a question. Are there any technical limitations that don't allow you to support nested parallelism? No, we could support nested parallelism, it's just more complex. And so far, we haven't had a good reason to implement that complex scheme. We are looking at implementing 3-level parallelism, where you get the outer level over the parallelism over blocks, inner level parallelism over warps, sorry, middle level, and then inner level parallelism of a warp through SIMD. But that is currently under development, and that already is kind of more complicated. But we could do nested parallelism, nested parallels, and actually have them really have, all of them have multiple threads in various ways. We could do that, one way or another, but it's just more complicated. And at some point it's unclear if it's worth it. Oh yeah, so this is how you get these, the nice code, and what we have a lot of remarks that help you to help the compiler to tell the user if something happened or not. And we have a lot of assumptions for the user to help the compiler do all of these optimizations. Because if the compiler fails with any of them, you usually end up with suboptimal performance. So we have these remarks that tell you, hey, I did this optimization, everything good, or I tried to do it and didn't work because of these reasons. Can you help me? And then it tells you where and what the problem was. And then you can go in and modify the code or use these assumptions or these command line options to help the compiler optimize your code. And that's kind of important. When we run the performance here again, upper left corner, now XSBench is actually really close to CUDA performance. So before that, it was still off, but now we gave it another 1.41x speed up, so another 40% improvement. And now we're really close to CUDA. Our SBench is still at CUDA level as it was before. Test snap, a 50% improvement, and on mini FFM, another 80% improvement there, which is still not CUDA level, but close. So you see that all of these things kind of get us closer and closer to CUDA performance while still maintaining portability and an arguably nice level to write things, because you don't have to manually put stuff in shared memory, you don't have to manually deal with synchronization and so on and so forth. Okay, so I'm going to run out of time soon. So I'm going to just introduce a couple of non-standard things that we were working on really quickly. One of them is remote GPU offloading. So initially you have one GPU, you offload your OpenMP stuff to, and you're happy. But then you have two GPUs in your computer. So what you do is you just, you ask OpenMP for the number of devices, and then you iterate through the devices and you offload your code onto one after another. That's fine. Now you can utilize with one program all the devices in your computer. But what if you want to use more than two GPUs, or more than 6, or more than 8? The solution so far has always been use MPI, right? Multiple nodes, then you use MPI, and then you can use more devices. But the code, what you see here, give me the number of devices, iterate through the devices, and then offload to that device. Actually, all of this doesn't make the assumption that the devices are local. This code has not necessarily baked in the fact that these devices are in your local machine. So your devices could also be in a cloud. And this actually works pretty fine. So if you want to scale, you can just use like the GPUs of other people. And if we did this in Theta GPU, we have a paper at ISC here. And when you see the XSBench strong scaling benchmark there, we went to 120 GPUs. And 120 GPUs cost us, like in the best case, so these are 3 different configurations. In the best case, it costs us like a 2x overhead per GPU, basically, compared to offloading only to 8 local ones. So the overhead is somewhere there for the distributed computing, but we can actually scale nicely. I mean, a 2x overhead per GPU is actually not that bad. And this is just a prototype. It's not to say that we couldn't make this faster. Okay, let's skip how this is done. Let's go to the next one. So this is OpenMP of compilation as it is right now. So you have OpenMP code, you pipe it through Clang. It is split into device compilation and host compilation. On the device side, you put in the OpenMP runtime on the vendor runtimes, and then you embed that into the host object. And at runtime, you can execute that on the CPU, on the virtual GPU, on AMD or NVIDIA GPUs, right? So we currently do not support Intel GPUs, but it's something that is coming. If people are interested in helping us getting Intel GPUs up and running, please contact me. So this is kind of the picture of OpenMP offloading right now in LLVM. Now, first thing we did is we built a math library that allowed you to do actual math function call optimizations that LLVM knows, for example, sign of 0, 0 on the device, which is great, which actually helps. Second thing we did is we allowed CUDA device code to be compatible with OpenMP offload code. So if you have a CUDA device library, for example, to do random number generation implemented in CUDA, you can link that into your OpenMP program and call the CUDA device functions from your OpenMP target region. Works great. And then you can run that. Okay. But what we really want is what happens next is we realized, we can call these CUDA device compilations, but why do we have to stop there? So what we did is we actually made LLVM OpenMP a portability layer, a target independent portability layer for languages. And through these wrappers on the right, the API wrappers and the built-in wrappers that we provide, we can take a CUDA program as it is, regular CUDA program, and compile it onto the OpenMP runtime. So it actually will use the OpenMP runtime for offloading. And why would we do that? Because then we can execute the CUDA program on the host, just like that. We can just execute it on the CPU and debug it there. We can use GDB, Valgrind, all of it. And we can also compile the CUDA program to an AMD GPU. Take a regular CUDA program and just run it on an AMD GPU. Now, we have done this as a prototype for CUDA. We haven't done it for HIP and SICL, but the same idea applies there as well. So when we get to provide the API and built-in wrappers for HIP and SICL, the same idea applies. You can take HIP code and run it on the virtual GPU, later on the Intel GPUs, and so on and so forth. So no more, all of it will be lowered to target the OpenMP runtime, and OpenMP runtime will actually be your intermediate layer. So you don't actually have to port your programs anymore. You can keep them and also mix and match them. You can have parts in CUDA, parts in SICL, and parts in OpenMP, and it will work together just fine. Okay.
Johannes, we have a quick question.
Yeah.
Are there any technical limitations that don't allow you to support nested parallelism?
Oh, I tried to answer that earlier. No. It's just complicated. So we don't have a good reason to do it so far. We could, it's just a lot of hassle for an unclear benefit.
Thanks.
Okay, let's finish this up. We're running out of time. So what did you see? You saw that we kind of worked on this GPU debugging and profiling. Actually, I didn't show you the profiling part, but that is also available. And then we added a virtual and a remote GPU offloading. So you can offload onto the host into a virtual GPU or onto GPUs on other computers. We have these optimizations that bridge the gap from CPU execution to GPU execution model, and that give you a big performance boost. We have this co-designed optimizations with the portable runtime that allow us to reuse one runtime on various platforms, including the host, AMD, NVIDIA GPUs, and at the same time, optimize away the runtime in the runtime state in a reasonable way whenever possible. Right now, we're submitting a paper on JIT specialization, so you can specialize your kernels with runtime values. And you can do link time optimizations, and especially important if your program is spread out over multiple files. This is really important to also enable all the other techniques that we had before. And then we have this, what I showed at the very end, this fully portable and interoperable GPU codes where you can mix CUDA, HIP, SICL, and OpenMP and compile everything onto the OpenMP runtime to then port it to whatever architecture OpenMP supports and mix it in a way you want. Now, this is kind of what I showed so far today. There's other stuff going on. Right now, I mentioned that earlier, we're looking at this 3-level GPU runtime where you have SIMD for the warps, parallel for multiple warps, and then teams for multiple blocks. And this will be combined with an OpenMP advisor that helps you to pick the features and utilize the runtime in the best way. So it will tell you, by the way, you should set the following flags or add the following clauses to disable or enable certain things that will make your program faster because you don't need the special handling, or you can promise the compiler certain things. So this was going to come soon. we're building this record and replay part where you can extract OpenMP target regions from a big program and then execute them in isolation later on. That allows you to do tuning on them and debugging on them without having to rerun the whole application and MPI and so on. Based on that, we're doing super optimizations on kernels where you can get, you spend a lot of time optimizing it, and then you get a speed of light estimate. How fast can your kernel go in the best case? Give me a second, I have someone at the door. Sorry. We want to really get into smart development in runtime environments. So where you have, where the compiler helps you to develop your software, gives you hints and feedback about the way you did it so far and what you should do better, helps you to interpret error messages and performance results and so on and so forth. But that is kind of far in the future and planned. Okay, obviously this is not all. There's more stuff that I'm not going to go into, but that kind of finishes everything. And if you have any questions, feel free to ask now.